Recall that we had previously learned about the standard matrix of a linear transformation. So specifically, if T is a linear transformation from Rn to Rm, then T is a matrix transformation. With standard matrix A, where the columns of matrix A are just the transformation of the standard basis of Rn. Okay, but specifically, this only works for a linear transformation from Rn to Rm. If we have a linear transformation from some vector space V to some other vector space W, and these could be abstract vector spaces or subspaces of Rn to Rm, then this does not need to be a matrix transformation in the same way. However, we just learned about isomorphisms, and we just learned that any finite dimensional vector space of dimension n is going to be isomorphic to Rn. And so we could use that to kind of find a matrix transformation that's going to tell us the same information as any linear transformation from one vector space to another vector space. Okay, so let's let V and W be vector spaces. With bases B equal to V1 to Vn, and C equal to W1 to Wm. Actually, yeah, M. Okay, so that means vector space V, vector space W, they're both finite dimensional vector spaces because they both have finite bases. Okay, V is an n-dimensional vector space. W is an m-dimensional vector space. Okay, so here's the strategy. So we start with our two vector spaces, vector space V and vector space W. Okay, now what transformation T does, it's a linear transformation from vector V to vector W. Okay, but we know that vector space V and vector space W are both finite dimensional vector spaces. So they are both isomorphic to R to a power. Okay. Do this one. So let's let this be Rn. And we know V is isomorphic to Rn because they're both n-dimensional vector spaces. And W is an m-dimensional vector space, so it's going to be isomorphic to Rm. Because they're both m-dimensional vector spaces. And because it's an isomorphism, it's invertible, so we could go in either direction. Okay? So let's in particular, if we have some vector v here, then applying the transformation this way, we will get t of v, right? And let's let these isomorphisms be the isomorphism to the coordinate vector of v with respect to the basis that we've already defined in the vector space. So we're going to go to the coordinate vector of v with respect to basis b. And here we're going to go to the coordinate vector of the transformation of v with respect to basis c. Okay? Now, we can define a new transformation, t prime, that goes from Rn to Rm, that behaves just like transformation t. T prime behaves just like transformation t, but we're just going to vector spaces isomorphic to our original vector spaces v and w. Okay? And because this is a transformation from Rn to Rm, this is a matrix transformation. Okay? So specifically, we get something like the transformation of, let's call it t prime of the coordinate vector of v with respect to basis b is going to be equal to some matrix A times the coordinate vector of v with respect to basis b. And what it's going to give me is the coordinate vector of the transformation of vector v with respect to basis c. Okay? Okay. So what we've done is we've discovered, hey, there's this m by n matrix A that gives us the information we need to describe this original transformation. It doesn't do it in exactly the right way. We have to use this isomorphism. But notice if I go this way, okay, apply the isomorphism, find the coordinate vector of v with respect to the basis, and then go this way, apply the matrix transformation, and then go this way, do the reverse of the isomorphism, okay, find the reverse of the coordinate vector with respect to c, we end up at the same point as if we just went this way. Okay? So we call this matrix the coordinate the standard vector of the standard matrix of t with respect to bases b and c. All right, so let's summarize what we've just discovered. Let's let v and w be finite dimensional vector spaces with ordered bases b and c. Okay. Suppose t is a linear transformation. Then we let A be the matrix where the columns of matrix A are the transformation of the vectors in basis B, but they're the coordinate vectors of that transformation with respect to basis C. Okay? Then we have this property here, matrix A times the coordinate vector v of any vector v with respect to basis B in vector space V is going to be equal to the transformation on vector V, but the coordinate vector of that transformation with respect to basis C. Okay? We call matrix A of this theorem the matrix of the transformation with respect to ordered bases B and C. So there's a lot going on here. It's probably a little confusing. Let's jump into an example so we can get a feel for what's going on.